Hi everybody, it's Mike Weaver here, Associate Director for Sigma-HSE. We're just waiting for the final minute to see if other people are going to join, and then we'll start the presentation. You have to bear with me because I went down with a very bad sore throat last night, so I'll try not to cough and hopefully my voice will hold out. Right, I think we'll get going now, as it's now 3 o'clock UK time, that is. So as I said, my name is Mike Weaver, Associate Director for Sigma-HSE, and the point of the webinar today is looking at developing a basis of safety for powders and dusts in Pacific. A little bit of background about us. We're a group of companies with headquarters in the UK, and we're dedicated to the provision of technical services and health, safety and environment to industry. We consist of 3 main units: Sigma-HSE in the UK, based in Winchester, down south in the UK, and that's our head office. And then we've got 3 units in India, that's Mumbai, Delhi and Hyderabad, where our test laboratories are based. And then we have a unit in Boston in the USA. Our areas of expertise, well, we bring together UK, Indian and USA experts to provide global HSE services. And we're looking at cost-effective engineering solutions for you rather than just give you a result or a report. We undertake laboratory testing in our UK laboratories to ISO, BSEN and ASTM individual test standards, and the work is divided between consultancy, testing and training. Part of that training is what you're involved in at the moment. Our Indian laboratory also looks at powder testing and works again to international standards. Technically wise, we have highly qualified engineers, scientists and chemists, and these people have worked in all areas of industry, and they now work for us and provide an expert source of information and knowledge. They're experienced professionals, and they sit on standard committees like myself on the Fire and Explosion Committee. The experience is working with global industries. Our engineers at the moment are all over the world, and we work globally as a company. We also work nationally. If you're in the UK, then we can go and see you. If you're in America, then again, and in India, we can have engineers to you, but we also work in countries where we're not based. We experience in diverse sectors, so areas like pharma, food, chemicals, oil and gas, utilities, personal healthcare, etc. As it says, we work in all these areas, and we can provide expert input to your problems. We have dust, gas and vapor fire and explosion testing laboratory, as I said, in the UK. We deal with all those areas of testing, including electrostatic testing, which is solely in the UK. But in India, we can look at dust testing as well, providing fire and explosion test data for you. We also have a chemical reaction hazards laboratory, or CRH lab, as we call it. And again, we have a whole range of equipment there, from DSC, ARC, Curious Tube, ARSST, etc., and a reaction calorimeter. We work under EN 17025 quality accreditation, and we are the only, from what my knowledge is, we're the only company in the UK that operate under those quality standards. Our consultancy team, well, we provide a wide range of specialist technical knowledge, including industrial fire and explosion hazards, things like ATEX, DESIR, etc., or whatever applies in your country, following the American guidance as well. We do electrostatic audits if you've got a problem with electrostatics, or we can look at your company for electrostatic and tell you whether you have got a problem that you might not be aware of. And we have highly qualified engineers that can try and sort the problem out for you. Other areas are something like PHAs, QRA, hazard, HAZOP, etc. And we look at functional safety, LOPA, SIL determinations. And we organise training workshops either on site, public, or things like webinars like I'm giving you now. So, off with the introduction, and now let's get into the nitty-gritty of the talk. We're looking at a basis of safety, and whenever you're looking at especially problems to do with fires and explosions, this is your ultimate aim, to put together a basis of safety so you can show to the regulatory authorities and your work staff that you are working safely. So what is a basis of safety? Well, it's a combination of measures relied upon to ensure safety. It's not just one thing. You look at a whole range of things to get this combination together. It highlights the aspects of design and operation which are safety critical. Overall safety strategy can be applied to things like equipment, the process itself, the area where the process is located, and work instructions such as standard operating procedures, etc., or following equipment manufacturers' guidelines. In order to build a basis of safety, it is necessary to have information available. So a typical list, if we came in on your site and we were developing a basis of safety for you, we would like to see equipment specifications. We'd like to consider what operating procedures you have in place to ensure that your staff are well trained and operate the equipment safely. We can review your hazard area classification drawings, and of course with those drawings you should always have a report which tells you how those drawings were produced. Maintenance procedures are always necessary because we need to know how you work. How do you maintain your equipment? What are your procedures in place for it? Such things as what materials are being handled. Are they flammable liquids only, flammable dust, combination of the two? And have you got data on them? For instance, powders, we would look at minimum ignition energy, layer ignition temperature, maximum ignition temperature, the KST or dust constant, Pmax, etc. And always remember that with the world's shortage in materials, many companies are turning to new suppliers. This means that some of the material properties may change. You may get finer materials or not so fine materials. They may be slightly different in their outlay, and therefore it is always advisable to retest these products if you do change your supplier, especially on a global scale. So building an effective basis of safety. We start off with the equipment. So this could be any type of equipment from a pump, silo, mixing vessel, etc. Procedures, operation and mechanical. Standard operating procedures are common in industry, and nearly every company has them in place to ensure their staff are well trained on the use of their equipment and materials they're handling. This will go into the box basis of safety. Deviation from normal operating conditions or processes. Again, it could be that someone's saying, look, we want to up the pressure. We want to change the temperature. We want to speed up the process because it's Friday and we need to get the results by the end of Friday. If this happens, then you have to include this into your effective basis of safety. So you may have to review it and change accordingly. Human factors. Well, these are debatable. As you can see here with the Simpsons, they can be extremely intelligent or, in this case, very stupid. So you have to factor these things in. How can a human being affect what is going on with your basis of safety? One of the advantages of a human is that if you're used to using the equipment, you can smell things, you can sense things are not right by your hearing. You may hear a rattle in the equipment or a grinding sound, which won't be picked up till later by sensors, but the human can pick it up. On the other hand, the human being can do the absolutely amazingly stupid things, and these have been known to happen quite frequently. So you have to look to see how much you rely on human interaction with your processes. Material properties. Here's a few pictograms of the sorts of things you'll be looking at. In the instance of fires and explosions, as I explained to you before, you need the data. If you're working on avoidance of ignition sources, how sensitive is the material to ignition? Without that information, you cannot build your basis of safety. Therefore, again, that goes into the box. Risk level and tolerance. Do you have a high risk that you can deal with, moderate risk, or a low risk? It depends where you're located on a lot of the times. For instance, if you work in a greenfield site in the middle of nowhere, you may not mind your explosion vents going off every day if you explain it to your staff. But if this is in a town next door to housing, you can't afford to have that happen. You know, we've had instances where a silo is on a hill and below it is an infant school. Again, there, you can't have any risk at all. You have to double brace everything to ensure you work safely. You cannot afford to have an incident. And of course, there's many more. When you start looking at your processes, you may find other things which interact with the way you work and could affect the basis of safety. We're looking at fires and explosions, and there's three types of basis of safety for fire and explosions. First one, explosion prevention, achieved by avoiding the flammable atmosphere. This could take out the fuel or take out things like oxygen or even the ignition sources, which is far more difficult to do. Avoidance of ignition sources. Make sure that any ignition sources don't become active and don't become effective. Well, that's the most important thing. You can have an active ignition source as long as the energy is not strong enough to ignite your fuels. So, does it become effective? And an often case for fires and explosions to do with dust and powders is explosion protection. It reduces the damage to plant and protects employees from the explosion. So the conditions for a dust explosion. Well, firstly, the powder that you're dealing with has got to be flammable or combustible, and in the case of an explosion, has to be airborne to form a cloud. As per liquids, the concentration must be within the explosible limits. Interesting here that we only take the minimum explosible concentration. We don't have an upper. That's because with powders, you get it's not homogeneous, and therefore you may have an explosion concentration occur when a bulk of product comes through a line, for instance. You must look at the particle size distribution. If it's finer, then it's more capable of propagating flame and explosion. The level of oxygen around needs to support the combustion, so you need to have an answer about that. You may work under reduced oxygen levels, but how low do you have to go to save your plant from blowing up? And you must have a sufficiently energetic ignition source, as I said before. So down here we have the fuel, an ignition source, effective that is, and an oxidant. And then we get the fire triangle. If we add mixing of the oxidant in the fuel and we confine, then we get the risk of an explosion. So why is flammability testing so important? A lot of people say it's a waste of money. A lot of people say it's expensive. A lot of people say they haven't got material to use for it. Lots and lots of excuses out there not to get it done. But at the end of the day, it's cheaper to get the testing done than to rebuild your plant because you haven't had it done and you don't know how to protect yourself properly. There's nothing worse than living with limited information to be able to make sure you're safe. So you require it to understand the explosive properties of your materials. You may need it for the sensitivity of your materials to different types of ignition sources, such as mechanical, electrical, electrostatics, heat. You can help you determine whether you can stay outside the flammable limits. As I said, the upper is more difficult, but you may be able to work with good extraction below the MEC. And it's actually a legal requirement on European safety data sheets as of 2021. Testing can be split into 3 sections, as I said before: explosion prevention, avoidance of ignition sources, and explosion protection. With regards to the safety data sheets, or the SDSs, Annex 2 of REACH has been mended concerning the compilation of safety data sheets on the 1st of January 2021. And now it's a legal requirement on these sheets to include data, flammability, MIE, LIT, MIT, PMAX, KST, etc. Lower and upper explosion limits, that'll be for liquids and gases, but for dust you want the MEC. And for liquids you may get the flash point auto ignition temperature as well. But these are now compulsory. So just pulling out powders and dusts, what are we going to look at? Well, you've got a whole range here. We can start with minimum ignition energy, which looks at electrostatic and mechanical ignition risk. Minimum ignition temperature considers dust clouds on hot surfaces. Layer ignition temperature considers layers of powder on hot surfaces. And explosion protection or violence, you get the maximum explosion pressure, the dust constant, KST, and the dust class. ST is Staub, so German, so you get K, ST, dust constant. MEC considers flammable range, minimum explosive concentration. LOC, limiting oxygen concentration if you're thinking about inerting. Burning behavior considers the fire risk. A lot of people forget this one and leave it out because they don't think their powder burns. But actually, in my time of testing, I've seen 3 or 4 materials go down 100 millimeters of powder in less than 5 seconds. So yes, they can burn rapidly and severely. Resistivity considers electrostatic issues and looks at equipment specification for zoned areas. The charge relaxation time complements the resistivity and lets you know how long a material can hold its charge for. And then you've got thermal stability. This is different to the chemical reaction hazard side of life. It's looking at bulk powders most of the time to see what happens when they're bulked up. What sort of temperatures will they decompose at? And we've been to many fires where a silo has caught fire because people don't have that thermal stability data. So let's look at explosion prevention first. Well, the Group AB classification test, you can see here the tube that we do it in, similar to the minimum ignition energy tube. We use the same piece of kit. Determines whether a material will form a flammable atmosphere when dispersed in air as a dust cloud. Therefore, if it does, you're then subject to DSIR and ATEX, which is Dangerous Substances Explosive Atmospheres Regulations, and Atmospherique Explosif, which is the French for explosive atmosphere. This would be in the EU where these directives come, but we're finding more and more countries around the world are using this approach to ensure their safety. So we get two categories. One is Group A, flammable or explosive as a dust cloud, and Group B, non-explosive or flammable as a dust cloud. Because it's a Group B doesn't mean to say it won't ignite as a powder layer though, so be aware of that. But Group A, you're covered by DESIR and ATEX, Group B you're not. And these are conducted under British Standards EN ISO 80079-20/2 2016. So, limiting oxygen concentration is the minimum allowable concentration of oxygen in a mixture of dispersed combustible dust. And you mix it with air and inert gas, in which an explosive atmosphere will not occur. So it's generally higher than for gases, typically 10 to 15%, although some pharmaceuticals I've been involved in have gone down to 4%, which is extremely worrying as a lot of people use 5% as their basis of safety. In these instances, 2 or 3 times pharmaceuticals have gone down to 4%. So it pays you to get it tested just to make sure. We use nitrogen as the inert gas, but you can use a program to convert over for CO2, water, etc. It's conducted to BSEN 140344 or ISO EN 170. We're ISO accredited for this test. If you look at the table there on the right, you'll see quite high: rye flour 13%, organic pigments 12%, methyl cellulose, all the way down to aluminium, which is 5%. But as I said, some pharmaceuticals have been even lower. Explosion prevention can also look at the minimum explosive concentration. It's the minimum quantity of dust dispersed in air that is required to form a flammable atmosphere. It's measured in the 20-litre sphere test, and no prizes for guessing why it's called the 20-litre sphere test. Sometimes the MEC is referred to as the lower flammable limit for powders. Again, under 14034, this time section 3, 2006. Typical example there on the right, 2 meters away from a 25 watt light bulb, 40 grams per cubic meter, you can't see the light bulb. Whoever came up with that, I'd like to meet them because I haven't got a clue why they use that. But we have had dust MECs down to a lot lower than that, down to 20 grams per cubic meter. So the next one, we've gone through explosion prevention. Now looking at avoidance of ignition sources, a separate type of basis of safety. Here we have taken from EN 1127. You can see 13 effective sources of ignition spaced out around there. Really, in reality, we only tend to look at about 6 to 7 of these things, but we do take note if we're in areas where you may get visible and HF electromagnetic radiation, for instance, or you may get radio frequency electromagnetic radiation. So in some instances, we may need to add to this, but normally it's about 6 to 7 that we concentrate on. Electrostatics, well, this is the minimum ignition energy. It's the lowest spark energy that can ignite the optimum mixture of fuel and dust, and this is it. It ignites the optimum mixture. Every mixture has its ignition energy, but it is only one MIE. Normally, for electrostatic discharges, you would find the capacitive discharge method of being used, purely capacitance. So this is similar to a human being sparking. This is purely capacitance. Be careful if you find out that some companies offer the VDI method of testing, and they may give you the mechanical spark instead, the inductive discharge. Sometimes these can be a factor of 10 lower than the purely capacitive one. So be very careful when you get the data. You should only use the inductive discharge method for mechanical sparking, not for electrostatic discharge. Any ignition source with an energy greater than the material's MIE is capable of providing ignition to the flammable atmosphere. In Europe, it's BSEN 13821 of 2002. And we've also got 80,079-22 2016, which is the electrostatic Bible in the EU. Typical values here: starch 100 to 300 millijoules, glass reinforced plastic dust 30 to 100 millijoules. We have sugar 10 to 30, though very fine sugar can go down less than 10. Aluminium 3 to 10, and active pharmaceutical ingredients down as low as 1. In fact, we've had them lower than 1. So again, you have to be careful with your products and understand what you're working with. Some are very high, 500 millijoules plus. You may not have a concern with them, but the lower the ignition energy, the greater risk you're dealing with. Talked about the minimum ignition temperature, MIT. This is the lowest surface temperature that can ignite the optimum mixture of fuel when dispersed in air. MIT is basically the auto-ignition temperature for dusts. So you have AIT for liquids and you have MIT for dusts. It's used to calculate the maximum permitted surface temperature of equipment, and you can operate in the range 200 to 700 degrees C. We conduct it to BSEN 50281/2/1, and again, you can find it in the ISO 80,079-22 2006 standard as well. Complementing the MIT is the LIT. This looks at layers as against dust clouds. LIT is the lowest surface temperature that can ignite a 5mm layer of material. LIT is used to calculate maximum surface temperatures of equipment. And if you want to do this, you must combine it with the MIT value. The range is 200 to 400 degrees, and it's to EN 5028121. And again, back to the 80,079-20-2 of 2016, which considers all the testing that we do in the EU. So just go back to that quickly. What we do to look at the maximum surface temperature of enclosure is we take the LIT value and we remove 75 degrees off of it. That's one temperature. And then we take 2/3 of the MIT value. That's the other temperature. Whatever's lower, that one decides the maximum surface temperature of enclosure for the equipment. So most common ignition sources, electrostatics, well, the risk is normally quite high due to some dusts having very low MIE values, down to less than 1, similar to gases and vapors. You consider flames and hot work. If you have these around, the risk is high, but often these are covered by operational procedures to stop flames being present and control hot work temperatures. Hot surfaces, risk is moderate as many values of MIT and LIT are quite high, although some materials do have much lower values, such as sulfur or sulfur salts. These can be as low as 200 degrees. And electrical sparks. All electrical equipment must be suitable for use for any given flammable dust. So you must look at the hazardous area classification and the material you're putting through in that area. A high level of risk is mechanical sparks. Here the risk of ignition is quite high. especially when you have low MIE values. As I said, you do this test with inductance and combine it with the MIT value. So looking at the dust explosion risk here, you can see we've got mechanical, overheating, open flames, electrostatics, welding, electrical, and others, which no one's managed to find out what caused the problem. Overall, there's about 40 dust explosions yearly across the world. This can result in injury and loss of life. You may end up having plant repair, compensation, and reputation, because a lot of people don't want to work with a company that's blown up their plant. It causes business interruption and loss of the market, because while you're not producing, someone else jumps in and sells their product. And of course, you've got the insurance company. The insurance is not too happy with reinsuring you if you've just blown your plant up through negligence. So let's look at hot surfaces and temperature classes for dusts. As I said to you before, these involve two pieces of kit. The maximum surface temperature of the equipment is decided with the LIT or MIT of a worst case material that you're using. The temperature class of the equipment exists so that it can be properly specified for this application, and this will tell you what temperature class the material can be in, the equipment can be in. So if dust clouds are likely, then the Tmax is less than 2/3 of the MIT. If dust layers are present as well, then the Tmax is also less than 75 degrees off of the LIT. Usually, because the LIT it leaves the material for a longer period of time, this ends up giving you a lower result. So normally the LIT tends to constitute the maximum surface temperature. Mentioned flames, smoking, and hot work. Well, hot work should be controlled by permitting. This is quite common today, and it should be the norm across your factory where you work. People should not allow to be working with hot work or flames unless they have a permit to do so. And a word of warning here, it's not a case of just issuing a permit. Before you issue the permit, you need to find out in detail what materials are being in that area. Are there materials still left in the equipment when they finish, etc. So it's not a case of just writing out a permit. You need a lot more information on it before you allow people to use flames or hot work in that area. Make staff aware of the hazards to avoid likelihood of common ignition source problems. Talk to your staff. Explain how these materials ignite. Get companies like us in to give a short training session for technicians or people working with these powders so they have an understanding and they're not scared of it, because they understand you understand the problems and you're handling them correctly. Not so common today, but smoking must be banned in hazardous areas, in fact right across the factory, and only permitted in designated areas. Often control all access to hazardous areas. In other words, if people are working in hazardous areas, you need to control the movement of people in and out. Electrical equipment for dusts. Well, electrical apparatus in hazard areas must be suitable for use in the area depending on the following. The MIT and LIT, as I said before, for surface temperature. Zonal classification of the area which it is to be located, whether it's zone 0, zone 20, zone 21, zone 22. You need to look at ingress protection, the IP rating, and the type of powder. Is it conducting or insulating? Conducting powders can be very dangerous with electrical equipment because they allow the electricity to flow across the powder. So typical one here is the European sign of conformity, The EX, which shows explosive atmospheres, Group 2, Category 2, dust. EX there, which means it's been tested properly and understood by a registered test house. And TB is the type of protection, 2C, so it's fairly low, temperature of 80 degrees C, and protection of dB. This is the typical sort of thing you will see on a label on a piece of electrical equipment. Electrical equipment must be installed and maintained by competent personnel. We recommend people who are Compact certified are the only people allowed to work in hazardous areas and wire up and put in and take out electrical equipment. As explained before, mechanical equipment. You saw the graph. This is number 1 on the list, and yet people ignore it. You cannot afford to ignore mechanical ignition because it is, as I said, one of the most common forms of ignition source. So, non-electrical, we would look at hot surfaces, flames and hot gases, mechanically generated sparks, electrical ignition sources, with the exception of stray currents and static electricity. Equipment in hazard areas should undergo a non-electrical equipment ignition risk assessment, or NERA, saying that you've looked at it for mechanical sparks and mechanical ignition, and the non-electrical equipment is as safe as your electrical equipment. How do you prevent mechanical sparking? Reduce the energy of the MIE of dust. Well, if you get a low MIE, the chances are you stand more chance of getting a spark. So the MIE needs to be as high as possible to stop the sparking. Use slow rotating equipment. Less than 1 meter a second is the norm, and if you can do that, the risk of ignition diminishes considerably. Make sure you've got things in place to remove trapped metal or stop it getting into the system and foreign body getting in. Consider externally mounted bearings and seals rather than internally mounted bearings. Control the material feed rates. The slower it goes in, the better. But often with your manufacturing processes, you need it in as fast as possible and out as fast as possible. So control your feed rates to what is feasible and possible. Have temperature monitoring in place on the bearings particularly, and to make sure that you don't get areas of heat. And look at maintenance, inspection and lubrication. Ensure your bearings, etc. are lubricated. Inspect to see signs of scraping. As you see the picture on the right, I actually took that a few years back, and the company didn't have an idea that the blades on this mixer were actually hitting against the end of the mixing vessel. This could have been pretty dangerous. And good housekeeping. Keep the areas clean. So, non-electrical ignition risk assessments. Quite a list of things we should look at. The European form of conformity marking, ingress protection ratings, know the speed of the moving parts. Consider earthing of the vessel. That includes things which rotate. These have to be earthed along with the stationary things. The materials of construction, is it made out of aluminium, stainless steel, plastic? Is it made of brass or what? Temperature rises and ratings of your equipment. Do you get sparks being emitted? Can they be emitted? Check out the equipment. As I showed you the previous one, they didn't realize that there was the blades were hitting the end, and the maintenance people hadn't even noticed it. Selection of materials to avoid electrostatic discharges. Normally you're stuck with what you've got. It's very difficult to avoid electrostatic discharges because you're producing a product and you have to stick with that product. Avoidance of frictional contact between steel and certain alloys. Make sure that you are aware of the different types of alloys. For instance, if you have a rusty blade and you hit aluminium, then you can get a thermite spark. Extremely incentive. Minimize the leak of dangerous substances from equipment. The number of times I see puddles and pools of dust and powder coming out of equipment. You're just expanding the area you need to consider and making it dangerous outside as well as inside. So get these things fixed. And the same with extract systems. Make sure they work properly, not full of duct tape and broken joints. Dust layers, the impact on temperature rise. We talk about 5mm layer on the MIT. The Americans, I believe, use 10mm. If you have 10mm of dust on there, then the layer will ignite at a lower temperature. Look at your operating procedures. Make sure they're in place. More than that, make sure your staff have read them and they're told what they involve. Look at maintenance activities. And here was another example that I was talking about. Maintenance just changed the bearings but didn't look at the fact the blades were hitting against the end of the vessel. Look at the operating environment. Is it salty near the sea? Is it near a potentially gas or vapor area, etc.? Have you got prevention systems in place? Do you have mitigation? If something does go wrong, can you mitigate the risk? Are you following manufacturer's instructions correctly? And has all the equipment been installed correctly by trained people that understand the equipment and know how to fit it in, including complex engineers to look at the electrical installations? Here we've got a short blender here. We've got a gearbox, rotating blades, hot surfaces, mechanical sparking, friction, electrostatics. So we've got hot surfaces, the motor body, the bearings, mechanical sparking, contact between the baffles and the casing, friction, impact and grinding sparks from the blades going round, electrostatics, because the blades are rotating and they could be metal, are they isolated? In which fact, you could have an electrostatic discharge. So static electricity. Funnily enough, out of all the ignition sources we have, this is mentioned explicitly in Desir and ATEX, is one of the ignition sources to be controlled. They believe it's the source of many ignitions, and when you look at that graph, the other may possibly be caused by static, but they can't prove it. It's generated wherever movement takes place. You see the examples there, pouring the powder, insulating liquids down a pipe, walking, insulating things going around a roller, sheets, spraying, and going into a blender type operation there where you're getting large amounts of static buildup. Always be aware it's often intrinsic to the process, and it's very difficult to eradicate if you have a lot of problems there. So how do we assess the static hazards? First thing you want to know, do you have a flammable atmosphere? If the answer is yes, then you need to look at charge generation. Can charge be generated on the equipment, isolated conductors, for instance, on the powder itself? And if you do get charge generation, can it accumulate? Can it, for instance, you may have a conducting powder which can generate charge going through pipes, and then you drop it into an insulating drum, and therefore the charge can accumulate in the insulating drum, even though it's a conducting powder. What quantity of energy is produced here? And what is the type of discharge mechanism that you're looking into to create an electrostatic discharge? So looking at static discharge mechanisms, corona is the least one of your problems. We don't often look at this. It's non-incentive for dust. And unlessly developing the sparks. Brush discharges, 3 to 4 millijoules. Even if your MIE of your dust is 1 to 2 millijoules, it's proven now brush discharges will not ignite any dust cloud. So you would only consider this for gases and vapors. The most common is sparks, charged isolated conductors discharged to earth or other conductors. It's calculated by E equals half CV squared, so the capacitance and the voltage produced are between 0 and 100 millijoules, sometimes bigger, but very rarely bigger. Gases, vapors, dust, mists, where the energy is greater than the MIE of the product. These are insensitive to dusts and have caused many explosions. If you're collecting powder into silos, for instance, then you may want to consider cone discharges. When you put your material in, at the top of your product, you see a cone of material. That's where the name comes from. If you get cone discharges, you'll see electrostatic arms or coming out from it, very bright, luminescent, coming off the surface of the material across the cone. They can be up to 150 millijoules, sometimes more, depending on the size of the silo, the particle size. This is where you don't want large insulating particles with fine dust above it, because this is when cone discharges become very dangerous. You can consider gases, vapors, dust, mists, again, where the energy is greater than the minimum ignition energy. And the worst of all is the propagating brush. Basically, a thin plastic insulating substrate on a metal backing. And this can happen not intentionally but unintentionally. For instance, we're involved in an incident where they were discharging plastic granules up a pipe into a silo, round a bend at the top, and on the bend it smeared the plastic. And there you go. This is a propagating brush discharge occur, which blew the pipe off, blew the silo up, and seriously damaged the tanker that was discharging. These can be up to a joule in energy or maybe more. I have seen one instance where cellulose tape was being produced and the waste was being put in a low load waste disposal unit, and the guy went to touch it, got the belt from a propagating brush discharge there by the cellulose laying along the metal container, and that put him in hospital. The whole of his arm blackened and his chest blackened. Extremely dangerous things. So, summary of avoidance of ignition sources. Consider all types of ignition source, but concentrate on the ones here that I'm just saying to you. Hot surfaces, you can see for powders and layers, flames and hot work, electrostatic, mechanical, and electrical. If you've got any of the others which you think are there, then you must consider those as well. So how do we go about avoidance of ignition sources? Perform hazardous area classification, ensure all the equipment is suitable for use in the zone, consider more detailed assessments for electrostatics, electrical and mechanical, etc. Control naked flames and hot work by a permit system. Obtain suitable flammability data. As I said to you before, how can you prove a basis of safety without it? It's impossible. Understand if a potential source of ignition can become active, and like I said before, can it become effective? And this all has to be written down in a basis of safety report, which is legible, readable, and not overcomplicated. So the final one we're looking at is explosion protection. You give the example, I expect you've seen it before, Imperial Sugar 2008, 14 deaths, 38 injuries, 14 with life-threatening burns, explosion fueled by an accumulation of sugar, and the place propagation caused this. No form of isolation, no understanding of the transference of dust cloud explosions. Basically a total ignorance of dust clouds and how they can damage and destroy plant and people. So for explosion protection, we get the 20-litre sphere. There's a picture of it there. Maximum explosion pressure generated in the explosion, the dust constant, calculate from the rate of pressure rise there. And explosion severity data is required when you're looking at venting, suppression, or containment. If this is used as a basis of safety, then you'll need explosion protection data to back it up. Conducted, as I said before, 14034-1 and also 14034-2. ST0, no explosion basically. Staub 0, Staub 1, between 0 and 200. Funnily enough, even though the sugar was classified as a weak explosion, it killed 14 people and blew a whole factory up. ST2, between 200 and 300 KST, what's recommended as a strong explosion: cellulose, wood flour, polymethyl acrylate, and the big boys. All of these are greater than 300. Very strong explosions: anthraquinone, aluminium, magnesium, the metals there. And the biggest one we've ever came up against was aluminium lithium hydride. And you know what that makes? Car batteries. And this is the biggest explosion by a long way. This came out at 3 times the explosion violence of a hydrogen air explosion. So yeah, if you want to get car batteries, this is what comes along with it. So mitigate the risks. If the risk cannot be eliminated or controlled, then you have to look at ways you can mitigate it. Reduce the number of employees, not often possible. Avoid the propagation of fires and explosions, one of the most important things. Explosion relief arrangements, you can use explosion suppression, or you can contain the explosion. Other such things as personal protection equipment. Take account of worst case always, and make sure you handle, store, and transport the dangerous materials properly. Explosion in a closed vessel, combustion of flammable liquids or dust creates hot gases. You can see with the graph here, you reach your Pmax and then it drops off again over a period of time. And the rate of pressure rise is the dP over dt, the rate of pressure over the time. And this involves the KST and the ST class. You can contain the explosion. Isolate pieces of equipment where explosions could occur. It needs to withstand the overpressure of the explosion. Good things about it: no release of combustion products or toxics, no requirements for provision of safe areas around it. But it's extremely expensive to build and maintain, requires pressure testing and associated documentation, and obviously the equipment is extremely heavy. You need to make all parts of the plant made strong, including the pipes, ducts, flanges, covers, etc. Must withstand the maximum pressure that is expected and maintain over the source of a lifetime. Your maintenance people have to understand why there's 27 bolts there, whereas when they're working under the normal plant, there's only 6. They have to be instructed to make sure all 27 bolts go back in. Strong plant is expensive to build and can be difficult to operate. The most common way of dealing with it is explosion protection is venting. This protects the plant and personnel from the effects of an explosion. It forms a controlled release of the pressure via weak open sections. The vent sizing is dealt with from the KST, which is the rate of pressure rise data in the 20-litre sphere. Pluses gives the ability to control the release location, normally outside the building in a safe area. Passive protection systems can be retrofitted to weak equipment, so you can put it in weak equipment. So the bad thing about it, combustion products and overpressure are released into the atmosphere. And one company I talked to, I asked them why they wanted the data for explosion relief panel, and it was going to blow highly toxic material over their car park. So it wasn't such a good idea to have explosion relief panels in place. I pointed this out to them. Non-flameless systems lead to explosion propagation. So the advantages, you can design it in-house, relatively cheap for the vent itself, needs little maintenance except for the doors where you need to make sure they can be kept clean, very wide range of application. Disadvantages, the material is released into the atmosphere, so it's unsuitable for toxic corrosives, must discharge outside the plant, so it restricts the siting of plant items to the walls, and large safe areas are required for the release of the gas and pressure. Flameless venting has come onto the market and it's quite popular in different industries. You can have the Q-roar, flam quench, etc. It stops the flame while allowing the vent. Efficiency is reduced because of the way the system is built compared to normal venting, and it needs to be type tested. It stops the flame coming out. That's why it's called flameless venting. But always be aware that high pressure and smoke can still fill the workplace, so try to keep it away from where personnel are located. And it must be sited in a restricted area. I've seen flameless vents with all sorts of things outside of them. Bits of loose equipment, cardboard boxes, all sorts of things, pallets, and the pressure coming out can blow these things up into the air and create a real hazard for people. It requires special maintenance as well, and it must be suitable for all materials. So sugar, for instance, it caramelizes and it blocks the vents. So you need to check this on a regular basis. Explosion relief doors doesn't require replacement after the explosion. They close up, easy to maintain and cheap to fit. You need to make sure the door doesn't close too quickly after the explosion. I'll show you why in a minute. Can weather badly. They're normally in outside areas exposed to all different types of weather. And the robustness can be compromised. And obviously, often they're not maintained properly. So they rust and you have collections of dust all over. This is what happens if the door closes too quickly. You can see here you get a vacuum. So be careful when you're using the doors. Hot combustion gases will cool down and create a negative pressure. Put a sealed container in a microwave, switch it off, leave it a couple of minutes and try to get the lid off. Quite interesting, because as the materials cool down, so the vacuum occurs inside the vessel. Flame propagation, as I said, these things need to be in special places, well away from people, forms of transport, etc., where most of the fuel mixture will be expelled from the vent and burn outside the vessel as a massive fireball. The length of the flame can be predicted. It could be 8 to 10 times V to a third. V is the volume of your vessel. So even a 1 cubic meter vessel can have flame lengths of 10 meters. But it won't reach more than 60 meters. And for gases, it's 5 times V to a third. Quite a substantial distance still. Width's difficult to predict, but there is a way you can predict for gusts. Typical vent problems, leaking and badly maintained vent. Someone's put a plastic cover with weights on over that vent. So it's got to be looked at and maintained properly. Don't just put it there and ignore it. So you've got explosion protection suppression systems. Extinguish the explosion in the early stages. Injection of pressurized suppression agent at given points around the vessel, as you can see. So there's no external effects and it's suitable for toxic, but it relies on effective explosion detection, highly specialized design, and expensive to put in. So no release of material, no restrictions on where you can put the plant, no flame propagation, well-designed system incorporates isolation. Disadvantage, high capital cost compared to vents, needs regular maintenance by the companies that's installed it, only works when operational. After activation, You need to recharge the bottles, etc., and you lose all your products. Typical pictures here with a fluid bed dryer and a dust collector. Isolation. As I explained with Imperial Sugar, the biggest failure they did was not put in isolation. This prevents pressure piling effects and flame jet ignition. Without isolation, the explosion in secondary vessels could be more than the first one. So basically, it's 2 times the initial start pressure. So if you got 7 bar in the first one, it starts off with an additional bar in the second one, you end up with 14 bar. So the secondary explosions are often the ones that do the most damage. 2 types of isolating equipment here: rotary valves, fast closing valves. So summary for explosion protection: always have the flammability characteristics of your materials. Review the SDS to see if there's other hazardous properties such as toxic. Review the hazardous area classification to identify where the equipment is located. Look at venting and suppression systems to be designed and installed correctly, as should fire protection. For containment, the vessel needs to be certified for use at expected pressures, and obviously I spoke about the maintenance. They have to be trained. Location may be a problem for venting. It has to be outside, and I've seen vents facing the building, facing roadways, facing, I've even seen it facing a canteen where people queue for the canteen. So be very careful where you put them. Confirm suitable isolation in place, again, often missing. Assess special procedures, hot work permits, management of change, permit to work, etc. Personnel working in hazardous areas should always be correctly trained. So, overview of the basis of safety: combination of measures relied upon to ensure safety, highlights the aspects of design and operation that are safety critical, many items to consider as we saw before: equipment, procedures, deviation, human factors, material properties, and the level of acceptable risk. For fires and explosions, normally 3 choices: prevention, avoidance of ignition sources, and protection. Explosion prevention, several ways to include this: change flammable material to non-flammable, not very often the case because you're making something. Remove the oxygen, pretty common. Inerting, especially with toxics. Work outside the flammable range for gases and vapors easily, not easy to do with dust, because you always get a slug of dust coming through the system, which takes you back into the flammable range. Avoidance of ignition sources: we talked about EN 1127, 13 potential ignition sources, but the most common: hot surfaces, naked flames, hot work and fires; electrical systems which are poorly installed and maintained; electrostatic discharges; mechanical sparking; and unsuitable mechanical equipment. Look at material properties. As we said before, without them you can't prove the basis of safety. Minimum ignition energy for electrostatics and mechanical ignition. You may also need further electrostatic properties such as powder volume resistivity, charge relaxation time, or chargeability, depending if the material is conductive, static, dissipative, or insulating. Consider the minimum ignition energy for mechanical ignition and hot surface. Layer ignition temperature for hot surfaces, 20 litosphere, absolute necessity to get the Pmax KST for explosion protection. And limiting an oxygen concentration, don't work on the 5%, get the information, then you know you're safe. So, hazardous area classification, very important. You know where equipment is, the type of class you're working in, how often is the material exposed to ignition sources. Consider all ignition sources there, including the top 5 or 6. And if necessary, you may have to do an electrostatic audit of the plant. Many times I've done this and found earth leads, flying leads, especially on LPG filling stations, which are there, but when you check them, the lead's broken and not connected. So again, these need to be part of your maintenance procedures. You need to include those. If the MIE seem to be low, or you've got gases or vapors present, definitely get an electrostatic audit done. Look at your equipment specifications and the suitability for use, your standard operating procedures, make sure staff are trained, do your risk assessments to ensure you know everything you want to know about the hazards of working with these materials. Consider material flammability, electrostatic properties, and thermal instability properties. Assess the process to understand manufacturing hazards, charging and discharge and mixing. Process maintenance procedures, hot work permits, managing with change, permit to work. And consider personnel working in hazardous areas should always be correctly trained. Determine what basis of safety can be used and confirm that it is suitable once all information has been analysed. And if you're going to have deviations, see if it still holds. Well, that's it. Overran just slightly, I'm sorry to say, but I hope you enjoyed the talk. If you need to contact us, then here's the details, and I wish you all the well for the future.